All right, this problem would fit very well into the previous homework assignment. We are given a couple terms of a sequence and a recursive formula. We're supposed to list some terms and then show that for every natural number, a desired formula holds. So let's get started by listing out the terms we are asked to compute, which are a0 through a5. Now, a sub 0 and a sub 1 were simply given to us as 1 and 2. Past that point, to get the next term of the sequence, we're going to take 6 times the term previous minus 8 times the term before that. So a sub 2 is going to be given by 6a1 minus 8a0. a3 is 6a2 minus 8a1. a4 is 6a3 minus 8a2. a5 is 6a4 minus 8a3. And now we just start computing. So as we were given that a0 is 1 and a1 is 2, we can plug those in right here and end up with 6 times 2 minus 8 times 1. 12 minus 8 is 4. Now that we know a sub 2 is 4, we can plug that in the next line. 6 times 4 minus 8 times 2. 24 minus 16 is 8. Now that we know the value of a sub 3, a sub 4 can be computed as 6 times 8 minus 8 times 4. Okay, since we had already computed a2 is equal to 4, I'm just plugging that in here. 48 minus 32, that's just 16. Now that we know both the values of a4, 16, and a3, 8, 6 times 16 minus 8 times 8. So 6 times 16 is 96. 8 times 8 is 64. 96 minus 64, 32. Okay, so having computed a bunch of terms in a row, we certainly seem to be getting powers of 2. 1, 2, 4, 8, 16, 32, maybe the next term is 64, etc. And that's exactly the formula we're attempting to prove holds for every index. Now the recursive formula looks at the prior two terms, suggesting we're going to do a strong inductive proof with two base cases. Okay. So for our base cases, we think we're going to need to do two of them, so I'm going to look at the two initial natural numbers, 0 and 1. So for n equals 0 and n equals 1, we need to prove that the desired formula holds. Now the desired formula would be that a sub 0 is hopefully equal to 2 to the 0, and a sub 1 is hopefully equal to 2 to the first. Now we were simply explicitly given that a sub 0 is 1 and a sub 1 is 2. So a sub 0 is 1 and a sub 1 is 2, and that does match. 1 is 2 to the 0 and 2 is 2 to the first. There wasn't much to do here. For n equals 0 and n equals 1, the desired formula holds, and we've shown that. Okay, now I'm going to slightly change up how the inductive part is shown, just so that it matches more closely how you may see other books or other presenters show this sort of thing. It's totally logically equivalent. I just want to give you a variety of options. So for the inductive step, we're going to assume that for some n at least as large as the final base case. Now the last base case we did was n equals 1. So next we're going to assume for some n at least as large as the final base case, 1, for every k from 0 up to n, the desired formula holds. A sub k really is equal to 2 to the k. So what we've done is we've assumed a sub 0 is 2 to the 0, a sub 1 is 2 to the first, a sub 2 is 2 to the second, all the way up to n, where n isn't specific, it's some natural number, but what is important is that n is at least as big as the last base case we did. So we've assumed the formula holds for everything up to n, and that's at least to the end of the base cases we did. Well, if we've assumed the formula holds for everything up to index n, okay, what we need to do is show that it holds for index n plus 1. So here's a mistake that a lot of students would make. They'd say, I want to find out what a sub n plus 1 is. We typically look at our recursive formula, and here they'll see an a sub n plus 1, and they'll try to solve for it by saying, for example, that a n plus 1 is a n plus 2 plus 8an all over 6. Now, while that is true, it is not helpful because we've only assumed things about the values of a sub k for index up to n, but not past n. So the appearance of index n plus 2 would be another unknown. Okay, what you actually do here, n is at least as large as 1. This means that I can take 1 away from n and still not be negative, which means n minus 1 is a legitimate index to use. If n is at least as big as 1, then n minus 1 is still a natural number. In this recursive formula then, instead of calling this index n plus 2, what we want to do is think a term of the sequence is 6 times the term before it minus 8 times the term before that. So here, the term of the sequence is index n plus 1. It's given by 6 times the term before that, which would simply be a sub n, minus 8 times the term before that, which would be index n minus 1. And as soon as you start subtracting from an index, you do need to be a little careful. But remember, n is at least as big as 1, which means n minus 1 is not negative. This is still a legal index to write down. So we assumed that ak equals 2 to the k for all indices up to and including n. So here is an index and here is an index that are up to and including n. Meaning I can replace an with 2 to the n, and I can replace an minus 1 with 2 to the n minus 1. Because we assumed this formula holds for all indices up to and including n. So a sub n is 2 to the n, a sub n minus 1 is 2 to the n minus 1. So for a sub n plus 1, what we're hoping to get out would be 2 to the n plus 1. If we can get there, we'll be done. Here I have 2 to the n. I'd like to turn it into 2 to the n plus 1, which means I'd like to factor a 2 into this. So 2 to the n times 6, I'm going to call 3 times 2 to the n. So this 6 I simply called 3 times 2. What about 2 to the n minus 1? If I want to change it into 2 to the n plus 1, I need to bring 2 squared into there. Thankfully, 2 squared can be factored out of 8. So I can call this 2 times 2 squared times 2 to the n minus 1. The reason I would do this is because in the first term, 2 times 2 to the n is going to give me 2 to the n plus 1. So the first term gives me 3 times 2 to the n plus 1. In the second term, 2 squared times 2 to the n minus 1 will also give me 2 to the n plus 1, and then I'll have an extra 2 hanging around here. Minus 2 times 2 to the n plus 1. If I have 3 apples and I take away 2 apples, I have a single apple left. So this all checks out. Okay, so the slight change in the inductive proof compared to how I did in previous videos. In previous videos, what I would have done is ended up with an an plus 2 here by simply assuming that for k equals 0, up to n plus 1, where k is at least as big as, where n is at least as big as 0. So by keeping the n being at least as big as 0, but making the list go up to n plus 1, then I would be able to use an n plus 2 here and just copy this recursive formula exactly. I sort of like doing it that way because it eliminates a mistake that I have seen innumerable students make over the years, which is in this technique where you assume the claim holds up to index n and then try to prove it for index n plus 1, in this recursive formula, if you attempt to solve for an plus 1, you're going to be led wildly astray. But this version is probably much more common, so I am going to use it in this video. Assume for some n at least as big as the last base case, which in this example was 1. For every choice of index up to and including n, the formula holds, then try to prove the formula holds for index n plus 1. You just have to be a little careful when using your recursive formula. So let's see another example. Okay, again, we're going to start with A0, A1, A2, A3, A4, A5, just computing a bunch of stuff. We were actually given 3 consecutive terms. A0, A1, A2 are all 1. Now let's look at our recursive formula. The next term is 4 times the previous term plus the term before that minus 4 times the term before that. So A3 is going to be given by 4A2 plus A1 minus 4A0. A4 is 4A3 plus A2 minus 4A1. A5 is 4A4 plus A3 minus 4A2. Now we can use the values we were given, which are all 1. A2 is 1, A1 is 1, A0 is 1. So this is 4 plus 1 minus 4. That results in 1. Now that we know A1 is 1, A2 is 1, A3 is 1, well, we actually have the same formula here. This is going to be 4 times 1 plus 1 minus 4, which is also 1. And then again, 4 times 1 plus 1 minus 4, which is also 1. So it really seems like what we're going to do is we're just going to see 1, 1, 1, 1, 1 forever. That's exactly what we are now going to try to show. For every index, a sub n is always just 1. Our recursive formula looks at 3 prior terms. So for our base cases, we look at the first 3 natural numbers. N equals 0, n equals 1, n equals 2. Our desired claim is that a sub 0 should equal, well, our claim is that every term is equal to 1. So hopefully a sub 0 equals 1, and hopefully a sub 1 equals 1, and hopefully a sub 2 equals 1, which was just explicitly given. There's really nothing to say here. Okay, next for the inductive part, let's assume for some n at least as large as the last index we took care of with our base cases, which was index 2. So for some n 2 or larger, for every k from 0 up to n, our desired formula holds. Then we need to show that the formula holds for the next index. Now, since n is at least as large as 2, this index is at least as large as 3, meaning this recursive formula can hold. So one term is given by 4 times the previous plus the one before that minus 4 times the one before that. So an plus 1 is 4an plus the term before a sub n would be a sub n minus 1 minus 4 times the term before that, and the term before a sub n minus 1 would be a sub n minus 2. Once we're taking things away from indices, we do want to be careful, but since we assumed n was 2 or larger, none of these indices, n minus 1 and n minus 2, are going to be negative. So we have assumed our desired formula holds for all indices 0 through n. And since these can't be negative, because n was at least as large as 2, all of these indices are between 0 and n. Certainly n is in that list. These numbers, n minus 1 and n minus 2, are less than n, but they're not less than 0, so they are somewhere in here. So by assumption, a sub n minus 1, and a sub n minus 2 are all equal to 1. And 4 plus 1 minus 4 is indeed 1. So having shown that if we ever have all consecutive values equal to 1 up to some index n, where n is at least as big as 2, then the next term must also be 1. And we manually showed that all of the terms up to index 2 are in fact equal to 1 because they were just given to us. Well then, the strong inductive proof kicks in and every term must be equal to 1. Another example, we start off with the computational bit. Okay, we're given that a0 is 1, a1 is 0, and a2 is 1. After that, the recursive formula is actually the same from the previous problem. So a sub 3 is 4a2 plus a1 minus 4a0. A sub 4 is 4a3 plus a2 minus 4a1. A sub 5 is 4a4 plus a3 minus 4a2. Okay. Now, since the recursive formula is the same, a lot of students are going to expect, well, all the values are the same. But in the previous problem, we were given 1, 1, and 1 as our starting values. Here we changed a single term. A sub 1 isn't 1, it's 0. And we're actually going to end up with a very different looking result. So let's get computing. So a sub 3 is 4a2, a2 was 1, plus a1, which was 0, minus 4a0, and a0 was 1, so we get a result of 0. A sub 4 is now 4a3, that's 0, plus a2, which was 1, minus 4a1, another 0, for a total of 1. A sub 5 is 4 plus 0 minus 4, which is 0. So now what seems to be happening is an alternation. 1, 0, 1, 0, 1, 0. Perhaps that goes on forever, which is exactly what this claim is about. When n is even, here we have -1 to an even power, which is going to be a 1, and 1 plus 1 over 2 is 1. But when n is odd, this becomes a -1 plus 1 over 2, which is 0. So as n goes back and forth, even, odd, even, odd, even, odd, this goes 1, 0, 1, 0, 1, 0. So this formula exactly says alternates between 1 and 0 according to whether n is even or odd. Okay. Since our recursive formula, as it did in the previous problem, looks at 3 prior terms, let's go ahead and do our base cases of the first 3 natural numbers, which are 0, 1, and 2. Well, for n equals 0, n equals 1, n equals 2. Hopefully, a sub 0 is equal to -1 to the 0 plus 1 over 2. Hopefully, a sub 1 is equal to -1 to the first power plus 1 over 2, and hopefully a sub 2 is equal to -1 squared plus 1 over 2. We were given that these values are 1, 0, and 1 respectively, and if we go ahead and compute these fractions, -1 to the 0 plus 1 over 2 is 1 plus 1 over 2. -1 to the first plus 1 over 2 would be -1 plus 1 over 2. -1 squared plus 1 over 2 would be 1 plus 1 over 2, and everything checks out. This really is 1, this is really 0, and this is really 1. So for the first 3 terms, indices 0, 1, and 2, we've manually shown that our desired formula holds. So we move on to the inductive part. So we assume for some n at least as large as the last base case, which again is 2, for all k between 0 and n, the desired formula holds. A sub k is equal to -1 to the k plus 1 over 2. Then what we need to do is show that the next term also obeys the desired formula. If we can do that, we're done. Okay, since n is at least as large as 2, n plus 1 is at least as large as 3, meaning this recursive formula holds just fine. So an plus 1 is going to be equal to 4an plus an minus 1 minus 4an minus 2. As before, since n is at least as large as 2, n minus 1 and n minus 2 are not negative, so all of these indices, n, n minus 1, and n minus 2, are between 0 and n. So for all of these indices, I can use my inductive hypothesis. So an is -1 to the n plus 1 over 2. an minus 1 is -1 to the n minus 1 plus 1 over 2, and an minus 2 is -1 to the n minus 2 plus 1 over 2. Now what we do is we look at what we are attempting to change this into. We are attempting to end up with -1 to the n plus first power. So we're going to use our trick outlined in the previous video, dealing with powers of -1. Okay, I'll just quickly remind us what it is in this box in the left. -1 to any power, let's call it the jth power, is simply -1 to the j plus 1. So remember, powers of -1 alternate plus or minus 1 depending on whether j is even or odd. So one way to think of this is if j is even, here I get a 1, but if j is even, j plus 1 is odd, here I have an odd, so -1 to an odd power is -1, but then I have an extra minus, so I end up with a +1 on both sides. Similarly, if j is odd, the left would be -1. If j is odd, however, j plus 1 is even, so this term would be +1, but then I have a minus in front of it. So this is always true. Okay. If you want to adjust a power of -1 by a single change, by adding 1 to it or going in this direction, subtracting 1. So adjusting the power of -1 by 1, just put a minus sign out in front, or if there was a minus sign, change it into a plus. Similarly, if you want to adjust by 2, just do that twice, but if I change a minus to a plus and then back, or vice versa, I don't do anything. Okay, or alternately, if j is even, so is j plus 2. If j is odd, so is j plus 2. So these are always equal. So if you want to adjust a power of -1 by 1, just change a plus to a minus or a minus to a plus out in front. If you want to adjust a power of -1 by 2, just go ahead and do it. It's going to be the same number. So we want to get out -1 to the n plus 1. Here we have -1 to the n. So I would like to adjust it by a single step, which I can do by putting a minus out in front. Next, what we have is n minus 1. I want it to be n plus 1, so that's an adjustment of 2 steps, which I can do for free. Then we have -1 to the n minus 2. I want to end up with a power of n plus 1, so I need to change this by 3 steps. So I can change it by 1 with the introduction of a plus. So if I do that again, introduction of a minus. So if I do it again, it would go back to plus, but if I do it a third time, it would go back to a minus. So this -1 to the n minus 2, I can turn it into a -1 to the n plus 1 at the expense of putting a minus sign out in front. Plus 1 over 2. Okay, every term has denominator 2. So I'm just going to collect this all into one fraction. Okay, now unfortunately I'm a little short on space, so I'm going to need to erase this just to clear up a bit of space. Okay, so putting everything over the common denominator of 2, we're going to end up with -4, -1 to the n plus 1, plus 4, distributing that 4 out. Then we have a -1 to the n plus 1 plus 1. Then we end up with a +4, -1 to the n plus 1 minus 4, distributing the -4 in the last term. So here we have a -4 of this power of -1 plus 4. Here we have a +4, -1 to that power minus 4. So observe that this 4 and this -4 cancel. Here I have -4 of a thing, and here I have +4 of the same thing, which is to say, this 4 cancels that -4, but this -4 power cancels this +4 times that power of -1. So the only terms that remain are -1 to the n plus 1 plus 1 over 2, which is exactly what we wanted. Okay, another problem with exactly the same recursive formula. an plus 3 is 4an plus 2 plus an plus 1 minus 4an. But again, we've changed our initial values. Instead of starting with 1, 1, 1 or 1, 0, 1, we're starting with 1, 2, 3. And the resulting formula that will hold for all an that we're going to claim is much more complicated. Okay, one mistake students sometimes make is thinking if the recursive formula is the same, then everything's going to be the same. That's not true. Okay, the recursive formula is the same, but if you change the starting values, you can get very different results. Okay, so we need to compute A0, A1, A2, A3, A4, A5. We were given 1, 2, and 3 to start with. Our recursive formula is the same, so this is going to be 4a2 plus a1 minus 4a0. I'm just going to go ahead and compute these now. 4 times 3 plus 2 minus 4 times 1. So 12 plus 2 minus 4, 10. 4a3 plus a2 minus 4a1. So 4 times 10, 40, plus 3, 43, minus 4 times 2, so 43 minus 8, 35. 4a4 plus a3 minus 4a2. 4 times 35 is 140, plus 10, 150, minus 4 times 3, so 150 minus 12 is 138. Okay, so these are doable. It's going to start getting worse from here, but thankfully this is where we're allowed to stop. With the same recursive formula that looks at the prior 3 terms, we're thinking let's do an inductive proof with 3 base cases, 0, 1, and 2. Well, for n equals 0, what we hope is that a sub 0 is equal to 9 times -1 to the 0 plus 1 plus 4 to the 0 plus 1 plus 35 all over 30. What we are given is that a naught is 1. Now what we have to do is simplify this formula down. 9 times negative 1 to the first would be a negative 9. 4 to the first would be 4 plus 35 over 30. And we can just check. 35 plus 4 is 39, minus 9 is 30, and 30 over 30 is indeed 1. Next, for a sub 1, we're given that it's 2. We are hoping that it's 9 times negative 1 to the 1 plus 1 plus 4 to the 1 plus 1 plus 35, all over 30. Well, if we compute all of that down, negative 1 to the second power is just 1, so this is a 9, plus 4 squared is 16. So 9 plus 16 plus 35, all over 30. Well, let's see, 9 plus 16 is 25, 25 plus 35 is 60, and 60 over 30 is indeed 2, so that also checks out. And finally, we were given a sub 2 is 3. What we're hoping to get out is 9 times negative 1 to the 2 plus 1 plus 4 to the 2 plus 1 plus 35, all over 30. And if we compute all of this, we get a negative 9 plus 64 plus 35 over 30. 64 plus 35 is 99. Take away the 9 to get 90, and 90 over 30 is indeed 3. So all of this checks out. Okay, I happen to know I'm going to need to reclaim some of the space for the inductive part, so I'm going to erase some stuff. Okay, but here we have the 3 base cases. It's just a matter of verifying that the desired formula does in fact match the value that was given. I'll point out here why I write things in the order I do. A lot of students, what they'll do is they'll simply start here and set it equal to a naught, and then simplify this down and get a 1. But by starting with this and setting it equal to a naught, you're essentially assuming that it works and then just doing some computation. The order this is presented, if we read from left to right, follows more logically. Why is a naught equal to 1? Because that was given. 1 is equal to this just as a matter of raw computation. Anyone who's reading can verify this equality, and then anyone who's reading can verify this equality, term by term, negative 9, 4, and of course 35. Similarly, 2 is equal to this. Someone reading will say, I guess it is. I mean, 9 plus 16 plus 35 over 30 really is 2, but why would I write it in that manner? Well, 9 is this, 16 is that, and then 35, and now we're just matching the formula. So if we read left to right, it flows more logically, in my opinion. This is given. This is just a simple computation, which is indeed equal to the formula we want, rather than starting out by declaring a sub 2 is given by this formula. We don't know that yet. We know a sub 2 is 3. Okay, anyway, I'm going to erase all of this work here just to get some space back, but we have indeed verified our base cases. So for n equals 0, 1, and 2, everything checks out. Now what we need to do is move on to the inductive portion. Okay, erase, 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 erase. Probably should have just used the select tool. It would have been faster, but now you can listen to me vamp. Okay. So next what we're going to end up doing is we assume for some n, okay, check, we did that, at least as large as the final base case for all k from 0 up to n, the desired formula holds. A sub k really is equal 9 times negative 1 to the k plus 1 plus 4 to the k plus 1 plus 35 all over 30. Then what we need to do is show that for the next term, it also holds. So this would give me a 9 times negative 1 to the n plus 1 plus 1 plus 4 to the n plus 1 plus 1 plus 35 all over 30. Okay. Now, since n is at least as large as 2, n plus 1 is at least as large as 3, so this recursive formula holds just fine. We're going to get 4 times the previous term plus the term before that minus 4, the term before that, and we just verify. Since n was at least as large as 2, n minus 1 and n minus 2 are not negative, so those indices do appear in this list of everything from 0 to n, meaning I'm going to be able to use this formula for index n, n minus 1, and n minus 2. Those are all indices where we have simply assumed that this formula holds. So we end up with 4 times 9 times negative 1 to the n plus 1, plus 4 to the n plus 1 plus 35, apologies, over 30, plus 9 times negative 1 to the n minus 1 plus 1, plus 4 to the n minus 1 plus 1 plus 35 over 30, minus 4 times 9 times negative 1 to the n minus 2 plus 1, plus 4 to the n minus 2 plus 1, plus 35, all over 30, close parenthesis there. Okay, we want a fraction all over 30. We have a bunch of fractions all over 30, so I'm not going to do anything with those denominators. Even if there were some 3's that I could cancel with certain terms, I don't want to. I want a denominator of 30, leave it there. Ultimately, what we want is negative 1 to the n plus 2. So here I'm going to need to adjust by one index, so I'm going to put a minus out here. N minus 1 plus 1 is just n, so this needs to be adjusted by 2 indices, and for a power of minus 1, that's free, so I can just replace this overall with n plus 2. Here I would need to adjust by 3 indices, so n minus 2 plus 1 would be n minus 1. To get that to negative 1 to the n plus 2 would be an adjustment of 3 indices. That's an odd quantity, so I would have to put an extra minus sign out in here. Okay, so equals 4 times negative 9, negative 1 to the n plus 2, plus 4 to the n plus 1, plus 35, all over 30, plus, this one I get to adjust for free. I'm only dealing with my powers of minus 1 for the moment, and simplifying the other exponents that I see. Minus 4 times all of this. Now when I change this to n plus 2, I did have to adjust that to a minus. Other things don't change. This is going to be 4 to the n minus 1 plus 35 all over 30. Okay, now what we're going to do is we're just going to distribute these 4's, collect everything over a denominator of 30. As in the prior problem, I happen to know I don't quite have enough space here, so I'm going to erase our equation that we're after, just so I have a little more space to work with here. So this is all going to go over 30. We end up with negative 36, negative 1 to the n plus 2. Now here, we get a 4 times 4 to the n plus 1. Then we have a 4 times 35. So that's distributing this 4 across all of these. Next, we just have a 9 times negative 1 to the n plus 2, plus 4 to the n plus 35. Okay. Here, we're going to get a plus 36, negative 1 to the n plus 2. Minus 4 times 4 to the n minus 1, minus 4 times 35. Okay, now we look for stuff to cancel. 4 times 35 minus 4 times 35. Those are going to cancel each other out in the numerator. We also have negative 36, negative 1 to the n plus 2, positive 36, negative 1 to the n plus 2. Those cancel each other out. And 4 times 4 to the n minus 1 is just 4 to the n. And now I have a plus 4 to the n and a minus 4 to the n, so those cancel each other out. Ultimately leaving us with, we have 9 times negative 1 to the n plus 2. We have 4 to the n plus 2. This term here didn't cancel out, and I'm going to absorb this single power of 4 in there now. And we have a plus 35. And that is exactly what we wanted. Negative 1 to the n plus 1 plus 1, 4 to the n plus 1 plus 1, 35 hanging off by itself, all over 30. Okay. So knowing where we are trying to go really helps inform what algebraic simplification we do or don't want to do. Because we knew we still wanted a denominator of 30, seeing a bunch of denominators of 30 is not scary, it's very nice. We're going to leave them alone because we want them there at the end. We never had to deal with that. And now we move on to the graph theory stuff. So construct a graph, directed graph, multigraph, or multi-directed graph, whatever is appropriate, given a vertex and edge set. So let's look at the edge set. These are ordered pairs. They are not just sets. Ordered pairs implies there's an order to them, so this is a directed graph. So this ordered pair says I'm going to draw an edge starting at A and ending at C. So let's just draw all of these vertices. A, B, C, D, E, F, G, H. I'm going to try to leave empty space. I really don't know. Let's put E there, F, G. I really don't know in advance if a bunch of vertices are going to have to cross or whatever. But now we're just going to kind of go in order. Draw an edge pointing from A to C. Okay. From A to C. There we go. How about from A to E? Okay. From A to G. From C back to A. So this actually points in both directions. From B to C. From B to itself, a little loop. From E to F. And from F back to E. From F to H. From F to A. From H to B. These cross, that's fine. And from H to C. That's it. That's really all there was to it. Notice that vertex D is hanging off by itself. It's not connected to anything. This isn't a connected graph. This vertex is in the vertex list, but there are no edges involving it, so D is just a little isolated point. Okay, that's all there was to this. Draw a picture of K5, K24, K33. K stands for complete. If there's a single index, single subscript, it just means on that many vertices, you're going to draw this many vertices and draw all of the edges you can. So for K5, I need 5 vertices, 1, 2, 3, 4, 5. And now these are simple graphs. I simply draw all possible edges between all possible vertices, and there you have it. Okay, so there's K5. When there are, however, 2 subscripts, it refers to a complete bipartite graph. So I have a vertex set with 2 and a vertex set with 4, and I draw all connections between the 2 vertex sets. So K24, I have 2 vertices on one side and 4 on the other. And from left to right, I draw all the vertices all the edges, that I can. Notice we don't have to go between these vertices or between these. Okay, this is a bipartite graph, so this vertex set connects to this one and vice versa, but these vertex sets don't connect to themselves. Okay, K33. We need 3 vertices on one side, 3 vertices on another, and then we just draw all the edges we can. That's it. Okay, here's a given degree list. Either construct a graph of whatever form you want with the given degree list, or explain why it cannot be done. Honestly, the only thing we have to check in any graph, okay, when you have 2 vertices and you draw an edge connecting them, it contributes a +1 to the degree of this vertex and a +1 to the degree of this vertex because you have a single edge connecting each one. Or if you have a single edge and you draw a loop, it contributes 2 because it goes out of and into that vertex. Anytime you draw an edge, it contributes 2 to the degree list, meaning the sum of all of the things in the degree list is achieved by adding all these edges up, but each one contributes 2. If I add up a bunch of 2's, I get an even number. So when you add up all the terms in a degree list, the result has to be even, and that's actually the only thing we need to check. So in this degree list, 0 + 2 + 2 + 3 + 3 + 4, there are 2 odd numbers, the rest are even, so 2 + 2 is 4, 8, 14, that's even, so this can be done. We have 6 numbers here, 0, 2, 2, 3, 3, 4. So there need to be 6 vertices. So 1, 2, 3, 4, 5, 6. And now we just need to try to connect them in a way. I'm just going to do a simple graph that has the given degrees. Now, we want a degree 0 vertex. I'm going to make this my degree 0 vertex, so no edges going into or out of this. 2, 2, 3, 3, 4. So if I do this, all of those now have degree 2. Okay? If I connect these two, I've made this a 3 and this a 3. So now I have a 2, 2, 2, 3, 3. I don't want 2, 2, 2, 3, 3. I need to change one of those 2's into a 4. So okay, let's not make it a simple graph. We weren't restricted to if I just put a loop there. So now I can label these degree 0, 2, 3. Down here is 3, 2, and degree 4. Okay, so we did get our desired degree list. Okay, this is by no means the only correct answer. There are lots of ways to do this. Okay, same problem. Here, however, 1 plus 2 is 3, plus 2 is 5, plus 3 is 8, plus 4 is 12, plus 5 is 17. So the sum of the numbers is odd. So there is no such graph. The sum of a degree list must be an even number. So this one just can't be done because the sum of the numbers in the degree list was odd.